here we're going to discuss some certain kinds of functions. We're going to talk about lines, we're going to talk about polynomials in general, and we're going to talk about quadratic functions. And we'll look at some properties of them. First, let's start talking about lines. The most important property of a line is the slope of a line. So let's just look at a line. We'll say that line. Now, the slope of a line, the line is increasing at the same rate everywhere. It's just a line. And the slope of the line can be defined by looking at 2 points on the line. We'll call them x1, y1, and x2, y2. And the slope, what we're defining as the slope, is a relation between how the x value changes and how the y value changes. The slope will be how much the y value changes for each unit of x value change. So slope of a line, we'll call it m, lowercase m, equals the change in y over the change in x. And if you want, you could, there are times where you'll be given 2 points and you can just think of the change in y as, well, y2 minus y1, the change in x, x2 minus x1. Or you could flip the 1s and 2s around in both of those if you want. There will be times where it's convenient to think of it as just a change, and there will be times where it's convenient to think of the exact numbers involved in the change. So let's look at an example. Find the slope of the line through, let's say containing instead of through. Containing these 2 points. These 2 points. 3, -2, and -5, 1. Well, the slope, we'll use this formula down here. Slope is given by the change in the y values, so -2 minus 1 over the change in the x values, 3. We start at this -2, so we're also going to start at this 3. Notice the subscript before the minus sign and the subscript after the minus sign are the same in the top and the bottom. So we have y value minus other y value over x value minus other x value. Notice here, 3 minus -5 is the same as 3 plus 5. And so we have this slope is -3/8. Now, to define a line, all you need are 2 points on the line, because the slope is going to be the same on the line. But notice, if you want an equation for a line, instead of choosing 2 specific points over here, you can choose 1 specific point and let this second point vary on the line. So let's let that x2, y2 be variable. If we do that, and remain on the line, we'll just say it is an x and y on the line. That gives us a different equation for the slope. So let's write this on the first board, because I probably won't have room on the fourth board. So let's say let's call this a remark. Remark. Letting x2, y2 vary gives us an equation for the line. Letting x2, y2 vary in the slope equation. So we're letting it vary on the line, and that would correspond to letting it vary in the slope equation. Letting it vary just means let it be a variable rather than a specific ordered pair. So letting x2, y2 vary in the slope equation gives this equation for a line. Gives this equation for a line. M equals y minus y1 over x minus x1. That's an equation for a line. But it's written as a fraction. It'd be nice to not write that as a fraction. So let's not write that as a fraction. And we can do that by multiplying both sides by that denominator. So multiply both sides by the denominator. Dry the chalkboard first. So letting that variance open gives us that. Removing the fraction gives us a nice linear equation for a line. So I'll say y minus y1 equals m times x minus x1. So multiply both sides by this denominator. Oh, was that in the way? I hope that's not in the way. It shouldn't be. Letting x minus, or multiplying both sides by x minus x1 will cancel it on the right side. And on the left side, you'll get m times x minus x1. On the right side, you'll get just y minus y1. I wrote that backwards because this is the standard way of writing this equation for a line. We call this the point-slope form formula for a line. And in calculus, we'll use a lot of what we do in calculus will actually be finding equations for lines. Maybe I'll erase this since it's in the way, even though I'm going to rewrite part of it in a moment. This point-slope form is very important, so I want that to be the only thing on the board right now. So right here, this equation gives us a formula for a line. Now let's look at why this is convenient. All you need for this formula is a point on the line and the slope of the line. In calculus, we will find that finding the slope of the lines in question will not be difficult if we use calculus. So if we have this formula for a line, where all we need is a point and a slope, we'll pretty much always be given a point. If you're given a point, then all you need to find is the slope. We will find the slope. There are many ways. Well, there's one large way of finding the slope that we will want in calculus. And we'll see that in Chapter 3 and Chapter 4. So right now, we have point-slope formula for a line. If you add y1 to both sides, it gives you the slope-intercept form for a line. That's used less in calculus. We might use it a couple times, but in general, we will use the point-slope form quite frequently. All you need is a point and a slope. So let's do an example. Example, find an equation for a line containing these 2 points. What were the 2 points in the previous one? 3, -2, and -5, 1. Find an equation for the line. Now, in calculus, we want equation for a line. What we need is a point, and what we need is a slope. So I always like writing down right at the beginning that we need a point and a slope. Well, a point, well, there are 2 points we could choose. You could choose either point. I'll choose the first one because it's written first. You could choose either one. It'll give you the same equation. Now, the slope we found in the previous example, which was -3/8. Was it -3? Yeah, it was -3/8. So we have a point, we have a slope, so we can find an equation for the line using the point-slope form. So an equation is what? Use the point slope form. Y minus y1. Y minus negative 2 equals slope. Don't forget the negative. Let's just rewrite that. Don't forget the negative equals negative 3/8 times x minus x1, x minus 3. You don't need a y-intercept. You don't need to simplify that. That's a perfectly nice equation for a line. So when you need an equation for a line, there will be a question probably on each test we do that just says, find an equation for the line given certain information. Your mind should immediately go to point and slope. Point and slope. Point and slope. Because with the point-slope formula, all you need are a point and a slope. I mean, finding the y-intercept, if you did that y-intercept way, what would you do? You'd find the slope, and then you'd do, what would you do? You'd substitute in and try to solve for b or something. And there's a lot of, in the standard finding the y-intercept way, there are a lot of computations you have to do, and a lot of computations where you could make a small mistake. Right here, the only computations where you can make a small mistake are finding the slope in that example. You could, I don't know, write a negative wrong or put a number in the wrong spot. But when doing the slope-intercept method, there are a lot of places, a lot more places you could go wrong. The next types of functions we'll talk about are known as quadratic functions. Quadratic functions are degree 2 polynomials. So a quadratic function is a function of this form. It's a degree 2 polynomial because the largest exponent on an x is a positive 2. There are no negative exponents. So we have an x squared term, an x term, and a constant, and all of them have coefficients. And we'll do a couple things with this. First, we're going to sketch some of these by using a method called completing the square. So I'm just going to erase this and start this example right on this page, or on this board. So use completing the square to sketch this function. We'll see that by completing the square, it'll reduce to one of the types of functions that we could have covered in the previous section, where we would use graph transformations. So example, sketch a graph of this function. F of x equals x squared. What were the numbers? Negative 4x and positive 9, using completing the square. So by completing the square. Well, let's talk about the method completing the square and how we'll use that here. So what our goal is going to be to turn this function into an equation that looks like an x squared with some graph transformations. Right here, this does not look like x squared with graph transformations. For example, that negative 4x is not any of our transformations. So what can we do to make this look like x squared with some graph transformations? Well, let's write it down. And then we'll do some work on it. Let's just put plus 9 there. So what we're going to do is add a number that allows us to write all of these x's as a perfect square. Now, if you add a number, you also have to subtract it because we're using this equals sign. Something on both sides of an equal sign must be the same. So I'm going to tell you and then explain why. We're going to add a 4. Now, if you add a 4, you have to subtract a 4. So what we're doing here is adding 0. Positive 4 and negative 4 make 0. Now, where did that 4 come from? Well, I'll tell you right now, it's not just this number with a positive sign on it. So where did that 4 come from? Let's draw an arrow to it, and let's see how we got that positive 4. Let's put the arrow at the positive 4, because that's the actual number we arrived at. Let's draw an arrow to the positive 4. Where did that positive 4 come from? Well, we look at this coefficient. So coefficient of x term. So let's say look at coefficient of x term. Well, here the coefficient of the x term is a negative 4. And what we do with that, we take the coefficient on the x term. So to find this 4, let's say to find that 4. That looks a little better. Look at the coefficient on this x term, which is negative 4. Take half of it. Half of negative 4 is negative 2. And then square it. Negative 2 squared is a positive 4. So this method, completing the square, will work for all of these, and we'll see why it works in a moment. But to find the number you add, you look at this coefficient, divide it by 2, and square it. That gives us a positive 4. That tells us to add that positive 4. Now, if we add a positive 4, we can't just do that because that changes the question, so we also have to subtract a 4. Because if we want this equal sign to remain true, the only number we can actually add is 0. And right here, since we added and subtracted the same thing, that is the same as adding 0. So we squeezed a 4 and a negative 4 in there. And you have to carry the 9 through because that's still there. That didn't go anywhere yet. Well, and why did we do this? Well, we did that because now this piece, these first 3 terms, x squared, negative 4x, and positive 4, can be written as a perfect square. In particular, they can be written as x minus 2 squared. So these first 3 terms are now a perfect square. That's why it's called completing the square, because it allows us to write all of these things with x as a perfect square. So these first 3 terms became x minus 2 squared, and we're left with a negative 4 and a positive 9. Negative 4 and positive 9 make a positive 5. So all we did here was we had to figure out a number to add that would allow us to write this as a perfect square. Well, right here, this function now looks like x squared with a couple transformations. So we can graph this. Remember, our goal was to sketch a graph of this function by completing the square. So we just rewrote this function as this by completing the square. So now let's sketch it using the graph transformations. Well, the first thing we'll do is start with an x squared. So f of x equals x squared. That just looks like this. Well, the first thing that happens to that is this negative 2. Remember what happens with that graph transformation. We start at 0, 0. This will shift that to the right 2 units. It'll move this point over to 2, 0. So that is now 2, 0. And then the last graph transformation takes this and lifts it up 5 units. And I'm just going to, I guess I'll squeeze this under here so I don't have to erase that. So it takes this, moves it up 5 units. So that point 2, 0 is now up here at 2, 5. And it's a parabola opening up like that. So what we did here was complete the square, look at the middle coefficient, or the coefficient on x, take half of that and square it. and then we did some graph transformations. Now, another thing we'll do with quadratic functions is find roots of quadratic functions. And what's a root of a quadratic function? Well, I'll define that in a moment, once I erase this board. So a root of a quadratic function, definition, or a root of any function. We'll look at roots of quadratic functions. Remember, a quadratic function is a degree 2 polynomial. There are polynomials of degree 3, 4, and so on. So a degree 3 would be where you have an x cubed as your largest term. We won't look at them in an algebraic sense too much. The algebra is more convenient with quadratic functions. And this is a calculus class, so we're not going to deal with too much tedious algebra. We'll deal with as much algebra as we need. So definition. A number z is called a root. A root is also known as a zero of a function if f evaluated at z equals 0. So if you take a number, you throw it into the function, it evaluates to 0, that's called a root of a function. So let's look at a couple examples. Find the roots of this function, or find the zeros of this function. X squared negative 4x plus 3. Well, we need to set it equal to 0. If we want the zeros of a function, if we want the roots of a function, we need to find where the function is 0. So let's set it equal to 0 and solve for x. Well, in this form, we can't really solve for x, but we can hopefully factor this, because 0 is a nice number. So I'm not going to write that like that, actually. I'm just going to rewrite this equation. X squared minus 4x plus 3. Well, can we factor this? Hopefully we can, and then we can use properties of 0 to our advantage. We need numbers which, what? Multiply to 3 and add to 4, add to negative 4. So we get what? X minus 1 and x minus 3. You distribute all that out, you get x squared, you get negative 1 and negative 3, which makes negative 4x, and then you get negative 1 times negative 3, which is positive 3. And we want to set this equal to 0. Now 0 is a nice number because there's only one way you can multiply and get 0. Well, there are two ways. If this thing is 0, or if this thing is 0. So if this is going to be 0, one of those two is going to have to be 0. This first one is 0 when x equals 1. The second thing is 0 when x equals 3. So we found those roots of this function. Let's do another example. I forgot the numbers even though I just looked at it. Find the zeros, find the roots of this function. Minus 3x and negative 10. Well, we'll try the same thing. We'll try the same thing. We'll try factoring it. So we need numbers that multiply to a negative 10, add to a negative 3. So what? 5 and 2 make 10, 5 and 2 make 3, and one of them will be negative. So we need a negative 5 and a positive 2. So this equals that. Negative 5 and positive 2 make a negative 3. Negative 5 and positive 2 multiply to a negative 10. And this equals 0. The only way we can multiply and get 0 is if one of the two is 0 or if the other one's 0. So this is 0 when x equals 5, or this is 0 when x equals negative 2. Now, sometimes factoring might not work. If factoring doesn't work, then you can do something else to find the roots. You can complete the square to find the roots of a function. So in these first two examples, we were able to factor. And to be quite honest, if we see any of these as we're doing our calculus, they will almost definitely factor. But what happens if they don't factor? Example, find the roots of this function. Negative 6 and negative 14, were those the numbers I wrote here? Yes. Find the roots of this function. Well, we can do this by completing the square. You could try factoring. It won't work. We would need numbers that, multiply to 14, add to 6. So 7 and 2, they won't make 6. 14 and 1 won't make 6. So this one will not factor. But what we can do is complete the square and work from that. Now remember what we do to complete the square. We look at this coefficient, which is negative 6. We take half of it and square it. Half of negative 6 is negative 3. Negative 3 squared is positive 9. And now you can't just change this question into a new one. We need an equal sign to be true. So if you add 9, you must also subtract 9. And then you don't want to forget that negative 14. Well, and we did that because now we can write these first three terms as a perfect square. So that these first three terms simplify to that perfect square. And then these other terms, 9 and 14, make what? 23. And there's a negative on them. And now we can set this equal to 0 and solve. Our goal, remember, I didn't write directions, but I said it out loud. Find the roots of this function. So now we have it in this nicer form, and we can set it equal to 0 and solve. So set that equal to 0, solve for x, so we'll add 23 equals 23. Take a square root. On both sides, take a square root. We'll need the positive and the negative because negative 23 squared is still 20, or negative root 23 squared is 23. And then we will, add 3. 3 plus or minus root 23. So we could have completed the square on any of these, actually. But if it factors, factoring usually is a little less tedious than completing the square. Now, you might ask yourself, do these methods that we just went through, does this method generalize? And the answer is yes, it does generalize if we want roots of a quadratic function. It generalizes to what is known as the quadratic formula. Now, up to this point, we did not have the quadratic formula. But now we will prove the quadratic formula. And I might take the entire board, so I'm just going to erase everything. My towel's getting dry, and it makes it not erase as well. Plus, these boards don't have anything holding them in on the left and right, so sometimes they slide all over the place. Well, I could put things on the left and right, but I decided not to. I'd actually rather they slide than not. So let's prove the quadratic from a theorem called the quadratic formula. The roots of this function, the general quadratic, are given by I'll write it here, I guess. What is it? It's negative b plus or minus root b squared minus 4ac over 2a. I would imagine most, if not all of you, have seen this before. You might not have seen a proof. So let's go through a proof. The proof is just completing the square, kind of like we did in this last example over here. But let's see how it goes. ax squared plus bx plus c. We're going to complete the square. In the examples we did with completing the square, the coefficient on x squared was just 1. And these are more convenient to do when that coefficient is 1. So let's first divide everything by a to get rid of that coefficient. So divide the first thing by a, you have just a 1 in front of the x squared. Divide the second thing by a, you get b over a. Divide the third thing by a, you get c over a. Okay, well now we need to complete the square. So let's complete the square. So remember how we complete the square. You take half of this coefficient and square it. Well, what's half of that coefficient? We have b over 2a. Let's just give the answer away. We have b over a, and we're dividing it by 2. Dividing it by 2, of course, is the same as multiplying it by a half, which of course is the same as just putting an additional 2 in the denominator. So we want half of this term, and then we want to square it. So we actually want this thing squared. So that thing squared is b squared over 4a squared. So we looked at the coefficient on x, took half of it, and squared it. I'm going to erase this so it's out of the way of the rest of the computation. So what did we do? We added a number. We can't just change the question, so we also have to subtract that number, because we want to add 0. 0 is the only number we can add and preserve equality. And of course, this c over a stays there. So all we did here was add 0. And we did that because now we can write that piece as a perfect square. The method completing the square, you'll notice this term that you get here is just half of this term. In the other two examples, that was true. In the first one, it was what, a -2? And the second one was a -3. That corresponded to what, the -4 in the first example and the -6, or half of the -4 in the first example and half of the -6 in the second example. So when you're completing the square, if you remember that process gives you a lot of the work you have to do. Because when you're writing it as a perfect square, all you need to do is write half of this term. So these first 3 terms can be condensed as that perfect square. But that's an A. And those numbers are still over there. So right now, this might not necessarily look more complicated, what was I saying? This might not look less complicated than the initial equation, but algebraically, it is more convenient if we're setting it equal to 0. which is what we're doing. So we want to set that equal to 0. I'm debating where on the board I want to do it. I don't think I'll have room over there, so I'm going to have to go back to the beginning of this first board. So I'm going to erase everything except that bottom line. And then I'm just going to rewrite that bottom line up here. So we have what? X plus b over 2a squared minus b squared over 4a squared plus c over a, and we're setting that equal to 0. So I just rewrote that line up at the top of the page. Okay. So now we just need to solve this for x. Just need to solve this for x. That's not necessarily a just with all these letters in front of us. That's part of the original statement up there. Well, how do we solve this for x? Well, right here, these are just numbers over here. Remember, those coefficients are all numbers, a, b, and c. So let's move them to the other side. Move that to the other side, you get b squared over 4a squared. Move this to the other side, you get negative c over a. And we can actually combine those fractions. Let's combine those fractions. The common denominator here is what? 4a squared. That denominator already has a 4a squared. To make this a 4a squared, you need a 4 and you need an a. So we'll put a 4 and an a on top, and you get 4ac. Well, okay. We still haven't solved for x, because now we need to take a square root of both sides. Take a square root of the left side, you're left with x minus b, or sorry, x plus b. Square root on the left, the square root and the square cancel. X plus b over 2a. I don't need the parentheses anywhere. What am I doing? I'm taking the square root, so I don't need those parentheses. Those parentheses were because we squared it. Square root on the left side gives us that. Square root on the right side. The bottom simplifies, because that's a perfect square, into a positive and a negative 2a. The top doesn't simplify. So we'll just leave that as the square root. But we have a positive negative on top and a positive negative on the bottom. So we'll just condense that as a positive negative on top. Well, we're almost done. We needed to solve for x. Now if we want to solve for x, I'll go over here. Subtract b over 2a from both sides. You're left with x on the left side. Subtract b over 2a from the right side, you get what? Negative b over 2a plus or minus b squared minus 4ac over 2a. And we can just write that as one fraction. They have a common denominator. And that gives us well, that proves this statement. So all we did was start with the original quadratic function and complete the square. Now, will I ask you this? No. I will not ask you to do this on a test. But it is useful to know that the proof of this is just completing the square. So I won't ask you this. There will be questions, well, there might be questions where part of what I write is do not use the quadratic formula. So there might be times I actually want to see you factor. But there's the quadratic formula. Proof is completing the square. So now let's use the quadratic formula to find roots of a function. So, example. Use the quadratic formula to find the roots of this function. Well, we'll use the quadratic formula. Remember what the quadratic formula says. We have negative b plus or minus root b squared minus 4ac over 2a, where a is the coefficient on x squared, b is the coefficient on x, and c is the coefficient on the x to the 0 term. So, in other words, c is the constant. So we have negative b. Negative negative 9 is positive 9. Plus or minus root b squared, negative 9 squared is 81, minus 4ac. 4ac, 4 times 3 times 2. 3 times 2 is 6, 6 times 4 is 24. And all of this is over 2a. 2 times 3 is 6, and we'll just subtract those numbers. 9 plus or minus 81 and 24 make what? 77 minus 20. Not 52, 57. All over 6. Root 57, that doesn't simplify at all. Yeah, you can't take anything out of it. Even if it did simplify, that answer's okay. Now, this question you couldn't factor conveniently. So in this one, you would have to use the quadratic, or you would have to complete the square, or complete the square in the form of using the quadratic formula. Now, we talked a little about polynomials. So remember, a polynomial, a quadratic function is a degree 2 polynomial. So they could have, any exponents that are positive. So they could have like an x to the 100th term. That's still a polynomial as long as you have all positive exponents, positive whole number exponents. But polynomials fit inside a class of functions known as algebraic functions. So we'll talk about a couple other algebraic functions. Definition. A rational function. Now, one point of clarification. On a test, I will not ask you any of these definitions, like definition of a polynomial, definition of a rational function. I won't ask these definitions from Chapter 1. You could be asked for a definition from a future chapter, possibly. But Chapter 1 is really setting us up so that we can talk about calculus. So right here, I'm setting up some of the definitions so that we can talk about these definitions in the future. So a rational function is of the form, we'll call it f of x. A rational function is p of x over q of x, where p of x and q of x are polynomials. So a rational function is a fraction of polynomials. So a couple examples. This will illustrate some polynomials as well. So examples, f of x equals what? How about x to the 5th minus 7x plus 4 over 5x squared minus 12x. There's an example of a rational function. Another example. F of x equals, let's see, negative 3x to the 24th plus 7x to the 12th, all over 5x to the 100th plus 1. That's also a rational function because in the numerator and the denominator are both polynomials. So these are rational functions. Polynomial over polynomials. Now, one nice property of rational functions is we can talk about their domains. So remember, the domain of a function is the set of inputs you can put into a function. Polynomials have no restrictions on their domains. So you can put any number you want in. But rational functions do have a restriction on the domain. For example, this one you can't put 0 into this function, because you'll get a 0 in the denominator. So rational functions have a potentially restricted domain. And we can see the restriction by looking at the denominator, looking at roots of the denominator, looking at where the denominator is 0. So let's do that. Well, let's look at, well, I'll state the result, then let's look at an example. So, it's a theorem. It's a small theorem, so maybe I shouldn't call it a theorem. Yeah, let's call it a theorem. In math, if you have a small theorem, it's usually not called a theorem. Theorems generally reserved for large results, but that's okay. The domain of the rational function p of x over q of x is a set of all real numbers such that q of x is not 0. So right here we have some math notation. Set notation uses these curly braces. So the set of all real numbers x, we'll assume just real numbers. The set of all real numbers x such that, so that's a vertical line that said such that. So this is the set of all x such that q of x is not 0. So anything you can put into this must satisfy that that the denominator is not 0. The numerator can be 0, that's okay. But what's bad is if the denominator is 0, because we can't divide by 0. So let's look at an example. Find the domain of this. Find the domain of this function. I probably should have said that. In the definition of a rational function, you should put where q of x, p of x and q of x are polynomials, and q of x is non-zero. If q of x is the 0 polynomial, then that fraction doesn't exist. So find the domain of this function. Well, all we need to do is find where the denominator is 0 and take that out of the domain. So let's set the denominator equal to 0. Here we'll factor this. You could use quadratic formula if you want. I think it actually would probably be easier to just factor it, because 2 and 3 make 5, and 2 and 3 make 6, or 2 and 3 make 6. So we want to set this equal to 0. This equals 0 when that's 0 or when that's 0. So the denominator equals 0 at -2 and -3. So if we want the domain of the rational function, well, then we have to take -2 and -3 out of our domain. So the set of x, well, maybe I should say, so the domain is, I mean, it's always good to answer the question that's being asked. Find the domain of that function. So the domain is the set of x such that x is not equal to -2 and x is not equal to -3. And we could write this in the set notation, or in the, this is the set notation. We could write this in interval notation, and I will write this in interval notation. So I'll say equals. In the interval notation, we want to avoid -3 and -2. arms don't extend long enough for me to have written that infinity nicely. There. So we took the entire real line, negative infinity to infinity, and we just jumped around -3 and -2. Either notation is fine. We'll see a similar application to this in chapter 4, I believe it is. So to this point we have what? We have rational functions, we have polynomials. One other type of function we'll talk about right now, and it's called a root function. So a root function is a function which is the root of something, a root of something. So we have a square root, could have a cube root, a fourth root, and so on. So let's define a root function. A root function is of this form. X to the 1 over n, where n is what? A positive number. N is greater, it's not 1 either. We'll assume that x to the 1 is not a root function. N is greater than or equal to 2. Maybe I'll just say n is a whole number greater than or equal to 2. Where n is a whole number greater than or equal to 2. So x to the 1/2, the square root function, is a root function. X to the 1/100th is a root function. So now one thing to notice is if n is even, then the domain is all positive numbers, because you can't take the square root of a negative number. You can't take the fourth root of a negative number, and so on. So I'll just write that as a remark. We'll say if n is even, then the domain of f of x equals x to the 1 over n is the set of all numbers x such that x is greater than or equal to 0. And if n is odd, then it's it meaning this. I don't want to write that again. Then its domain is all real numbers, because you can take a cube root of something negative. A negative times what? Itself 3 times is a negative. Is the set of all x. So I'll just say negative infinity to infinity. I'll use the intervals. So I'll say is negative infinity to infinity. So you could have just said the set of all x, but geez, that's not a brace. I was looking up here, or maybe I wasn't. I don't know what I was doing. I was thinking of something other than what I was writing. And when you're thinking of something other than what you were writing, you are more apt to make a mistake, like I did there. We have parentheses, not curly braces, on intervals. Now, we have polynomials, root functions, rational functions. Those make up, they make up a lot of functions. And with composition of functions, we can take a root function composed with a rational function, a root function composed with a polynomial composed with a rational function. And we can use that to create a lot of functions. And they're all known as algebraic functions. So let's look at this algebraic function. And let's find the domain of this algebraic function. And we'll use this first remark to do it. So, example. Find the domain of this function. So this function is what? It's a root function because it's a 1 over 2 in this case, x to the half. But it is a polynomial inside the root function. So what we did was actually a composition of a polynomial and a root function to create this. We have a square root function. So from this remark that I erased half of, we know the domain is going to be where the inside is greater than or equal to 0. So let's find where the inside is greater than or equal to 0. Okay, I'm going to add x squared to both sides and then flip the inequality around so it looks like this. Now x squared less than or equal to 16. It's the same as x being between 4 and negative 4. So the set of x such that x is between 4 and negative 4 is the domain. Now, well, let's write this as the interval. The interval is a little nicer in this case, because it's just one closed interval like that. Closed because we include the endpoints. Now, right here, going from here to there, requires some work. We will not do this much. The examples we see where we need to do an inequality with a quadratic will be just like this, where you can jump from here to there. Technically, you would have to use a sign chart. A sign chart is it's a device used for general quadratics with inequalities. That's an algebra topic. That is not a calculus topic. So the only type we will see are things like this, where you just have x squared is less than a number or equal to a number, and then you can jump to the answer like this by taking a square root and saying it's between the positive and the negative of the square root. You could do a sign chart argument. You won't lose credit if you do a sign chart argument, but we will not see any where we have to do a sign chart argument, because that's a more advanced algebra, and this is a calculus class. This is not an algebra class. We will do a good deal of algebra, but it's not an algebra class. So I'll end this first topic with a definition, a more formal definition, the definition of an algebraic function. So an algebraic function. Definition. An algebraic function is what? Involves, will be slightly informal. Involves what? It involves addition. It involves subtraction. It involves multiplication. It involves division. It could be a rational function. And it could be roots. An algebraic function involves that, and, well, we'll say or roots. So it will be the actual definition of an algebraic function is different. You can look that up if you want on Wikipedia. You'll see why we restrict it to this. So every function we've spoken about so far today, so far in these first couple videos have been algebraic functions. If it's not algebraic, it's called transcendental function. So I'll define that as well. A transcendental function cannot be described using these algebraic properties, or operations, I guess. A transcendental function cannot be described by basic algebraic operations. And we'll talk about some transcendental functions. So just you probably know some transcendental functions. Examples, trig functions. They are transcendental. Example, exponential functions. Are transcendental. Logarithms are also transcendental. And there are more. We'll just restrict that to this. So in this one we did quadratic formula, we did lines. Lines are very important in calculus. In algebraic, I won't ask you for these definitions, but these are words that could show up. So I won't ask you to formally define these, but I could ask you questions that involve these words.